So let me start by thanking the organizers for organizing this very nice event and giving me the opportunity to talk here. So I'll be talking about some related. So we have been hearing a lot of talk on many body localization. This will also be along that line. So let me first also acknowledge my collaborators. So this work is mainly done by Nilanjan, who must be here, and also Jagannath. So this work that I'm going to talk about also is, so this work is published in this publication. If you are interested, you can take a look. But this is also related with some other works that we have been doing over last 3-4 years. And I also acknowledge the collaborators in these related works, Shomi, who is here, Sitodhi also here, and David Logan from Oxford, and Subroto, who is also here. Okay, so again, so always I think all localization talks start with a slide like this with a picture of Anderson. So, basically the same thing that I mean, if you have non-interacting particles, quantum particles in a disordered potential, then you have these two radically different possibilities. I mean, you can either have states which are delocalized, extended over the whole infinite lattice, or you can have these localized states which are localized around certain points in space with some localization length. And the prototypical model is this model that Anderson wrote down, which is just a tight binding electrons hopping on a random potential distributed, let's say, uniformly with some strength W. Now, the Anderson transition, depending on the symmetry, let's say the standard case, you see it in 3 dimensions. And this transition, you can, in the non-interacting case, you can see both as a function of disorder strength or as a function of energy. If the disorder is not very strong, that is, some states of the band are delocalized and some states are localized. And the critical property of this Anderson transitions is same, whether you study it as a function of disorder or strength or as a function of this energy. And you will have a mobility edge, single particle mobility edge at this energy, and this you can characterize this kind of mobility edge essentially by looking into single particle states in the non-interacting case and characterize their properties. For example, what you can do, you can calculate the single particle IPRs. So you can take the single particle states, eigenstates, and then look into in the real space basis and construct these quantities, which are these generalized IPRs. And these generalized IPRs, given the number of sites n, goes like this. And depending on how it varies as a function of n, you can characterize delocalized state. In that case, it will, this quantity dq will be simply q minus 1, which essentially means that the state is, the eigenstates are spread over the entire lattice. So the typical one we do is this I2, which is the standard IPR. And if you have a localized state, then this dq will be 0. So essentially it means that the states are only spread over finite number of sites. And eventually you can also have states which are in between these two, the localized and delocalized, where dq is some number which is between okay, it should be q, q minus 1 here. But anyway, so let's say look at d2, d2 will be between 0 and 1. So now, so where do you see this multifractal state? So the one place where you see it is at the Anderson transition in the single particle case. So now, when you turn into many body localization, as we have been hearing also last week, so essentially the question of many body localization, as it was posed, is that you start with this non-interacting problem with all states localized in the band. So there is no mobility edge, all the states are localized. And then what you do, you introduce this interaction, some generic interaction, and you ask, and of course you have many particles, it's a many body system, and you ask whether localization still survive, and it's a non-trivial question, and that's why we have been working on this problem for so long. That when you put interaction, it essentially connects exponentially large number of states, and whether localization can still survive. And the early works on this, as we know, by Basko, Alainer, Alsular, and also similar time Gorny, Millin, and Polyakov, essentially use this perturbative treatment and depending on whether the interaction is weak enough compared to some scale related to disorder, you can show that some kind of locator expansion essentially converges and perturbatively, and then it will suggest that there is MBL. So this works of course didn't consider this rare regions effect which we heard about from the morning talk by Professor Imbri. And so in some sense we have seen or at least heard the arguments, the main arguments about this mathematical proof, which is very some mild assumption as far as I can understand, which also shows that you can have, I mean these rare region effects are may not be that important. In principle you can have MBL. But till now, the MBL, at least when you try to study it mostly numerically, especially if you are interested in MBL transition, then it has been studied by many people starting with this early work, and now we know that this kind of pictures that we have as a function of energy density and disorder, which is showing this MBL transition between volume law ergodic phase to area law MBL phase, should be really called a finite size MBL. Because it is not probably capturing this kind of resonances, long range resonances, long distance resonances within the system size axis. So in this talk I will be mainly just talking about this kind of system because I am going to only discuss numerical work, and certainly you can think about this work. I mean we will be using some finite size scaling which sort of tries to extend the small system effects to infinite size, but you have to really think about this way that maybe if you somehow can remove these resonances, then this is the extrapolation, but actual system these resonances will come and the values of these transitions and all will be changed, and maybe the critical properties. Okay. So now the main question that I am going to discuss here is, of course, it's not a new question. This has been asked over several years now, starting from these early works of MBL. That so if you start with a single particle non-interacting systems where you have a mobility edge, and now introduce interaction, can MBL still survive? Okay. So of course, there are a lot of works on this. I mean, first of all, people have shown that that if you have some, so if you start with some system which has some symmetry protected delocalized single particle state, then those can in principle delocalize all localized states, because and they cannot be localized themselves because they are protected by symmetry. So this of course is a case when you have either symmetry or topological protection. But in general, you can have a system where there is no such protection, and one of the examples which I am going to discuss is this generalized Aubrey-Andre-Harper model, which is basically has a quasi-periodic potential. And in this work, there are many works that have shown that at least numerically within this finite size MBL idea, that you can show that MBL can still exist even with mobility edge. Okay. So and not only that, I mean people have also shown evidences of states which are intermediate between MBL and ergodic states, which are called these non-ergodic extended states. So for example, if you want to characterize this non-ergodic extended state based on these studies, I can draw somewhat boring but I mean table like where essentially you can characterize this non-ergodic extended state which has entanglement entropy like ergodic state. However, they have some fluctuations of some operators which are like MBL states, and they are level spacing statistics in between MBL and thermal states. Okay, so this will be the characterization based on these earlier studies of these systems. Okay, so now one question, of course, that was asked, that how non-ergodic states are realized when you have a mobility edge, right? So what really happens to these localized states and delocalized states? And the way it was understood, at least based on arguments, locator expansions and other kinds of arguments by Rahul Nandakishore, is what is known as this MBL proximity effect. And the picture is somewhat intuitive and simple. Whether it's true or not, that okay, I mean you don't know, but certainly it has confirmation again from finite size numerics by these people. So essentially you can think about this MBL proximity effect having in terms of a ladder system with, let's say, two chains, one chain which is clean, which doesn't have any disorder, and another chain which has same size as this other chain, is disordered, and let's say in a localized phase, MBL phase, then the idea is that due to this coupling between the localized states in this disordered chain and the delocalized states, single particle state in the clean system, the delocalized states, single particle states actually can get localized by coupling to this localized state by seeing some effective disorder through this localized state. Okay, so that's what has been called the MBL proximity effect. So one of the questions that I'm going to ask, can you really see this? Right? Can you really see that single particle states of some sense are getting localized, delocalized single particle states are getting localized by the localized states? Okay, can you explicitly see this? And what I'm going to show is something what Arti talked about. You can actually see this at least within finite size by looking into single particle excitation. Of course, when you have many body states, many body system, interacting system, there is no meaning of single particle eigenstates, but you can still define excitations, single particle excitation. So these single particle excitations will adiabatically continue to the single particle states in the non-interacting limit. Okay, so you can ask whether single particle excitations are localized or not, whether they have a mobility edge in them. Okay, although there is no single particle eigenstates as such. So this is the idea. So the idea is that you start with this non-interacting thing with the mobility edge, and what I am going to show that you can have basically three possibilities. So one possibility which is the obvious one, that the delocalized states delocalizes the localized states and they remain delocalized. Yes. This is all 1D, yeah. So this is this quasi-periodic model where you can have mobility edge in one. Yes. So, so this is one consequence, that all single particle excitations get delocalized, and I will show that you will get a delocalized many body state in this case. The other case, which is like the MBL proximity effect, where all the localized states actually localizes the delocalized states, and then the many body states is MBL. And but you can have a situation which is in between, where actually you can see that there is a mobility edge in single particle excitation in the interacting system. So there is in some sense a single particle mobility edge even in the interacting system, and this will corresponds to if you characterize these states to this non-ergodic extended states. Okay, so you can basically connect this kind of Fock space and real space characterization. Okay, so plan for the rest of the talk is this. So I'm first going to discuss, so I'm going to use to study this system, so some exact diagonalizations and slightly larger systems. To access slightly larger system, I'm going to discuss some recursive Green's function method in the Fock space to characterize some Fock space properties. And for that, I'll discuss some connections between the real space and Fock space pictures that are around in the MBL systems, and how to look at MBL transitions. For example, in this Fock space picture, you try to characterize this Fock space propagator, and from in terms of this Fock space propagator, you can see the multifractality of the MBL states, and also you can construct a scaling theory again within finite size MBL. So most probably it's a crossover scaling which will eventually go away, but at least within this system you see quite sharp scaling. I'll try to describe this plot, and then using these tools and standard exact diagonalization, I'm going to discuss this effect that you can have a single particle mobility edge even in an interacting system, and how it corresponds to the Fock space properties. Okay. So let me just very quickly just tell that. So just to connect with the real space picture, so the real space, the way you understand MBL is in terms of these local integrals of motion. So where essentially starting with this Hamiltonian, you can define some integrals of motions for this case related to, let's say, the number operators, and the Hamiltonian essentially has all these conserved quantities. So all the quantities, this n tildes commute with themselves and with the Hamiltonian, as a result conserved, and these are local, which is the kind of construction Professor Imbri was trying to discuss, and then you can define in terms of the original basis, the side basis, you can sort of see that these are quasi-local. So these quantities have some weight support in local space, these local integrals of motions, which has some length scales, let's say zeta, and then they can have also interaction which in principle can have a different length scale. Okay, but these are all quasi-locals. Both interactions and their support is quasi-local. Okay, and general understanding is that this length scales actually doesn't diverge at the transition. So whatever transition we could study, it remains finite at the transition, and based on that you can actually construct this kind of questions which have been asked, that what is the critical property of the MBL transition. As we know from finite size studies, you can of course get some nice scaling and quite sharp transitions, but then the exponents that you get violates this kind of general criteria that you should satisfy, which Arti discussed. Okay. So because finite size numerics is insufficient, people have constructed this kind of real space phenomenological RGs. I guess one of those will be talked about in tomorrow. So the picture that roughly emerges from this real space RGs, phenomenological RGs, is this, that essentially if you look at the MBL transitions, it is characterized by these length scales, which is essentially some insulating inclusion in the delocalized site, whose size actually diverges as you approach the transition. And similarly from the thermal side also, so these are the early studies, and then it has been modified later. So from the thermal, from the localized sides, you have this thermal inclusion whose size again diverges. However, if you look at these Liomme length scales, they remain finite at the transition. Okay, so these pictures have been modified by including these avalanche effects, and then the critical property of the transition goes from being more continuous like to this KT type scenario. Okay, so now how do you see it in Fock space? Okay, so that's what we are. So I'm going to discuss. So to describe this Fock space thing, so what you try to do is you construct this Fock space graph. Now the Fock space graph, how do you construct, is not unique. You can construct it as a vertices of some higher dimensional cube or something, but this kind of construction turns out to be quite useful for numerical construction. So what you do here is that you construct this lattice, let's say for this system where it has number conservation. So what you do, you start with a state where all the particles are, let's say, on the left hand side. So you have half filling all the particles on the left hand side, and then you just start moving this particle whichever many ways you can do. And as you do that, this graph will sort of funnel out like that, and eventually it will reach a very fat middle slice. So basically you have these slice structures. Within each slice, the states don't have any connections. These connections only between one slice to the other slice. Middle slice is the fattest, and then eventually again you funnel in, and you reach a state where all the particles has gone on the right hand side. Okay, so this is how you can characterize this Fock space graph. Now, of course, the number of sites in this Fock space graph is very large. It's the same number that you face when you try to do exact diagonalization in this kind of basis, which I have indicated by these occupations, and I am indexing them with the index I, which is just saying which state it is. Let's say this is I equal to 1, and it will be I equal to e to the power n or something. Okay. So now once you write in this basis, of course, as we know, that's the matrix we diagonalize, that you can write this as a tight binding problem on the Fock space, because essentially it is just a hopping between these Fock space states from one state to the other, and then you have some on-site energies, and these on-site energies is basically the part which is diagonal in this number basis. Now what you can see that these on-site basis energies are of course random, but they are only constructed out of L random numbers, and whereas you have ultimately exponential in L numbers on the on-site energies on the Fock space. So it has to be extremely correlated, okay, because you cannot construct exponentially large number of random numbers with algebraically large random numbers, right? So it has to be extremely correlated. In fact, this correlation is very crucial, because if you really look at the Fock space graph, so most of the part of the graph actually has a coordination number which is L, and this L is diverging in the infinite system size. So if you just use standard Anderson argument for uncorrelated disorder, so this system can never really be localized, okay, because your coordination number is actually diverging. So only way it can do so is if you have correlated disorder, and this has been argued by many people, including Stitodi and others, and David Logan. So, that's the idea. So, and how do you characterize this? So, the typical characterization of this localization in Fock space is again the same, that you now construct a IPR on the Fock space. So, you write the eigenstates in the basis of this occupation basis states, and then you look at these coefficients in this basis, and then you just construct the same kind of thing. Okay, so what you find here. Here, so basically exactly what I said earlier for the non-interacting case, all you do is the same characterization. All you have to do there is just replace this number, real space number of sites by the Fock space number, the number of sites in the Fock space. Okay, and then you can have exactly same characterization. Now the question is that what happens to the MBL? So are they really localized in the Fock space? And it turns out that I mean, it is kind of obvious that they cannot be localized in the Fock space. There is a very simple argument to that. But this initially people sort of found it from numerical calculations, that whatever you see in the finite size MBL calculations, these MBL states has basically is like this fractal or multifractal. Okay. So this is actually obvious, because if you even construct if you take an Anderson localized state and put it on a Fock space, so you can essentially show that this IPR in the Fock space is basically the single particle IPR to the power number of particles. Okay, and that is just a multifractal, because it is e to the power minus n with a coefficient which is slightly smaller than 1. So it has obviously has to be multifractal. I mean, that is even true for single particle Anderson localization if you put it on a Fock space. So no way it can be localized on the Fock space. Okay. So now, so question is that how do you characterize this multifractality dynamically? So I have to go a bit fast here, because so what we do here. So I'll skip these details in much, not go into this thing much detail. So what we do is, given this non-interacting problem in the Fock space, which has this nice slice-like structure. We try to calculate this propagator. So rather than diagonalizing the problem, we directly try to calculate this propagator. So of course you have to do some regularization, and the regularization is quite tricky. You have to properly put a broadening which is smaller than the many body level spacing, otherwise the results will be completely messed up. Now given you have done all those things properly, so what you can so we characterize two things using this propagator. So first of all, using this diagonal element of the, so this should be inverse Green's function. There is a typo here. No, sorry, this is the Green's function. So basically you have this inverse Green's function, you invert it and you obtain the diagonal element. Now from the diagonal element you can show that the diagonal element can always be written as some bare element which is with the bare on-site energy and a self energy which is known as Finberg self energy. Okay, and what you look at is the imaginary part of this Filbert self energy. So this essentially gives you the decay rate of a localized state initially at site I on the Fock space. Okay, so this is what you calculate. And another thing you can calculate is the off-diagonal element of this Green's function on the Fock space. And from this, knowing the distance between the two Fock space sites, which is some kind of hopping distance, you can actually extract a Fock space localization length. Okay, so how the propagator decays in the Fock space. So we use, as I said, we use some recursive Green's function method. This is a very well-known method in studies of Anderson localization, which has been used by great success to characterize scaling theories of Anderson localization. Now here, since you have this slice structure, you can nicely use this method very easily on this Fock space. So essentially in this method, what you do, you start, let's say, with some block, and then you can add additional block and recursively recalculate all the Green's function, and you can just go on building this. And in this process, what happens is that only large matrix that you have to invert is the sort of the fattest slice. So you don't need to invert the full matrix, you sort of recursively invert it. As a result, it has a sort of a gain, numerical gain, which is only, of course, in the prefactor of some exponential. Eventually it is also exponential. But the prefactor, so this is the scaling of sort of the largest matrix that you invert, and the prefactor is pretty small if you do direct inverse. Okay, and that sort of can gain you a lot of this thing, and using this we can easily reach with much effort state of the art ED, which is quite sophisticated. Okay. So what we calculate using this is typical values of these quantities. Okay. So now, so very quickly, so this is not the topic of this talk, but so this is what will be discussed by Subroto day after tomorrow. So we have done calculations using this method for random systems, system with random disorder. And there essentially what you find is that you can characterize these finite size MBL transitions by noting this fact that if you are in a thermal phase, this rate of decay should be finite, because in thermal phase it should decay. Okay, so this self energy, the imaginary part of the self energy should be order 1 as the Hilbert space dimension goes to infinity. Whereas in the MBL phase it has to decay to 0 if there is a MBL. The question is how does it decay? So what you find, so this is the plot, so this is the MBL phase and this is going towards the relocalized phase. You can roughly see that it has reached order 1, and within these system sizes it is not varying much, and here it is actually decaying with some power law, NF to the power some power. Okay, and it turns out that so in the MBL phase it decays like this. So this quantity, that delta tau, so this imaginary part of self energy actually decays like NF to the power minus 1 minus ds. Okay, so it turns out that this ds is actually related to the fractal dimension that you can extract with from IPR. So this is like a dynamical manifestation of this fractality that you can directly extract from this self energy. And in certain situations you can show that they are exactly same. In certain situations they are not exactly same, but both characterizes this kind of fractal dimension. Okay, and in fact if you do some kind of finite size scaling, you find that there is in the MBL phase this quantity ds has to be less than 1 for a fractal state, is less than 1 including the transition, and then it jumps to 1. Okay, in the ergodic side. Okay, so so basically MBL states are multifractal. This I have already told that if you look at Anderson localized state on the Fock space, they will also be multifractal. Okay, this is kind of obvious. Now this is the picture that you sort of get from these calculations. So what you find, and I will not go into this. Subroto will discuss this. So essentially, what you find that there are two kinds of length scales. Actually, one length scale and one volume scale in the Fock space. So this volume scale actually has a, so volume scale characterizes sort of size of non-ergodic region, non-ergodic patches in the ergodic sites, and when you approach the transition, these non-ergodic patches take over the entire Fock space, and as a result you go to the MBL phase and it has this KT-like divergence. Whereas if you approach from the MBL side, then there are sort of kind of percolating paths which have some length, and this length scale actually diverges. Whereas you can show that this Fock space length scale, that a localization length, so this is a correlation length, but this is a Fock space length, localization length, it actually remains finite at the transition. Okay, like the Riom length. Okay, now let me, for the last 6-7 minutes, just let me discuss using these results, this the system with single particle mobility A. So this is the system that we study, which is this generalized Aubrey-Andre-Harper model, which was introduced by Ganeshan et al. So this model has a mobility edge in one dimension. So this, there are several models like this. We just took one of them. I don't think it matters. So this has some exact expressions of the mobility edge. So it had only one mobility edge. Okay, unlike the standard scenario where you see two mobility edges because of some duality between these delocalized and localized phases. So there is a single mobility edge which you exactly know, and we study this interacting system at quarter filling, which has been studied earlier, and these values of these things. Okay. Okay, so this is the standard diagnostic that I have already mentioned. I am not going to go through it. It's just showing within finite size system, you see that these non-ergodic extended states are in between the MBL and ergodic states. Okay. So now, so how do you detect? So I said that we want to see this mobility edge, okay, even in the interacting system. So how do you do that? So what you do here is that you look into local density of state in the interacting system. Okay, so you calculate the local density of state. So first starting with non-interacting system. So in non-interacting system, you can calculate using the single particle eigenstates. So now if you are delocalized, so then what we will find that if the states are delocalized, then your density of state, and Arsti was showing yesterday, will be a continuum. Okay, so you will basically have a sort of a continuous thing, and then in that case the typical value and the average value are roughly same and both non-zero. Whereas in the localized phase, you essentially, for local density of state, you have isolated poles. So the poles do not become a branch cut, and these poles only has measure 0. As a result, the typical density of state is 0 because you have mostly these gaps, right, if you look locally. So if you calculate the typical value, that will go to 0 in the thermodynamic limit, although if you average over all sites and all disorder, it will be non-zero. Okay, it will just give you average density of state, and average density of state will be non-zero, but it will be different from the typical value, which is 0. Okay, so this you can use to first in the non-interacting model to see the mobility edge. So what you have to do here, you have to look bit closely, and what you find that this is the non-interacting mobility edge. So if you look at the single particle excitations on left of it, what you find with system size becoming larger, the density of state is going down here. Okay, it's going down, whereas on this side they are initially maybe slightly going up. Basically they have converged to the average value. Now in this system there are also spectral gaps because they are quartz periodic system, and in the spectral gap you can characterize because the average density of state also goes to 0 as L goes to 0 in the spectral gap. So that's how you can characterize these dashed regions which are gap, these regions which are essentially localized. So typical value, this is logarithmic scale, typical value as you go L going to infinity, it will go to 0, whereas this will converge. Okay, so this is how you can characterize the mobility edge. So now let's do for the interacting system. Of course, you will be very limited by system size here, but even then you can still see this effect. Okay, so first of all is some region which has been characterized as ergodic in this model by earlier studies. What you find that roughly speaking, that as you increase L, so essentially this local density of state has more or less converged everywhere, L16 and 12 you can see. So whereas if you go to the what is called MBL phase, what you can clearly see that this local density of state is going down as you go increase system size, right. So this green is the largest system, it is going down to 0. Whereas if you see in the non-ergodic extended state, and I have just plotted the single particle mobility edge, on the left of it, you can still see that the density of state is actually going down as you are increasing system size, whereas on the right hand side, the density of state is going up and converging on the right hand side. So this is in an interacting system, you can actually see this single particle mobility edge. Okay. So using this. So now these calculations are very limited as I said by ED, so we can do slightly more using this Fock space method that I have mentioned, and result is roughly very similar to the random system transition that I mentioned between MBL and ergodic thing. So what you find here by this Fock space characterization of this, so this is the the fractal exponent that I extracted from this imaginary part of self energy. So earlier in the MBL state you found it to be fractal between 0 and 1. So here what you find that actually for the entire what has been called in earlier studies as the MBL phase, so this here we are studying as a function of many body energy density. So as you vary the many body energy density, at low energy density you have some MBL phase, and then you have non-ergodic extended state, then you have ergodic state. So what you find here is that this entire non-ergodic state, be it MBL or non-ergodic extended, they have basically same kind of fractality. You cannot distinguish them by fractality on the Fock space. There is almost no, I mean you cannot detect any transition here, okay, in the Fock space between MBL and non-ergodic extended state. I showed you that by single particle excitation you can detect them, right? So that's what I showed you. So you can do some scaling theory. I'll just skip this in the interest of time. So question is that how do you see in this Fock space diagnostic the difference between non-ergodic extended state and the MBL non-ergodic states, right? So it turns out the difference actually comes out in the Fock space localization length. So if you look at the Fock space localization length as a function of size, system size, so then what you find that in the ergodic phase as a function of system size, what I call the Fock space localization length, which is from the off diagonal element of the Fock space propagator actually increases as or changes with the system size. Okay, as you change the system size, the Fock space localization length change. Okay, and the same thing happens, slightly weaker, but same thing happens in the non-ergodic extended state. That means Fock space localization length changes as you change the system size. Whereas if you see in the MBL phase, the Fock space localization length doesn't change. Okay, so this actually can, I am just finishing. So this can characterize. So now the multifractality cannot distinguish the non-ergodic extended state from the MBL state, but it can distinguish all the non-ergodic states from the ergodic state. Whereas this localization length can distinguish between the ergodic state and non-ergodic extended state from the MBL state. So if you combine both of them, you can characterize these two. And in fact, you can see if you plot as a function of energy density, you can actually see that MBL phase, there is very little system size dependent. You get some system size dependent in the non-ergodic extended state and huge system size dependence in the ergodic side. Okay. So with that, let me essentially just conclude again with a boring table. So I just added some more columns to this table. So just to say that this non-ergodic extended state can be characterized in real space in terms of single particle excitations. They still contain a mobility edge or an indication of a mobility edge, at least within finite size numerics. Very likely that these are much more fragile than the MBL state when you go to large system size, and like MBL, you can ask about their fate. They will be probably much more fragile. So we cannot comment on that, but at least within finite size numerics, you see that they are characterized by same kind of multifractality as the MBL states. However, their non-local propagators in the Fock space are different between the MBL and non-ergodic extended state. So with this, let me thank you for your attention.
Do you see anything in the single particle level statistics that also suggests like this?
No, single particle level statistics is no. It's, I mean, single particle level statistics will not characterize this. Okay, so I mean, first of all, in the interacting case, how do you define single particle level statistics? Right, you cannot. So of course, if you look at the non-interacting model, yes, you can characterize this transition by the single particle level statistic. But interacting case, we don't have single particle levels, right? Only thing we can characterize is the single particle excitations.
Yeah, I was thinking whether we can just generate level statistics of these excitations.
No, you cannot. I don't know how to generate level spacing, single particle level spacing in interacting system.
When you look at the non-interacting system with this quasi-periodic potential, in the kind of system sizes comparable to what you did for the interacting system, so like 20 side chains or something, do you see any indication of the single particle mobility edge?
Little bit, much less. So the system size I showed, as you have noticed, much larger in the non-interacting case. So if you look at a smaller system size, I think Nilanjan may verify the effect is harder to see at those system sizes. But in interacting case, somehow you see much more clear-cut dependence. Yes.
Okay, so then maybe as a follow-up question, like why do you identify this non-ergodic extended regime as being due to the single particle mobility edge? If like
no, yeah. I mean, we don't have, I mean, yeah, so it's just a correlation, right? I mean, just an observation. So if you look at it, at least within, I mean, we can't really detect what is the exact mobility edge in the interacting case, but you can still see a quite distinct difference in the scaling, even with such small systems. And that correlate when you do this Fock space calculation or entanglement or other filter. So it's just based on that. It's, yeah, there is no, yeah, fundamentally you cannot connect these two.
Yeah, or just say like we've actually been working on the same model, so we should talk.
Okay, sure.
Curious to know. So suppose you have correlated disorder in your original Hamiltonian. Like, what are the consequences on the physics? Like, how does it change, for instance?
Yeah, so we have not, maybe other people have studied, we have not studied much correlated disorder. So only thing we have studied in another paper, which is if you take quasi-periodic, in the real space quasi-periodic potential, I mean you have seen the quasi-periodic potential has correlation, right, in real space. So and there, apart from this mobility age and other things, if you have a system, let's say just standard Aubrey-Andre model, and it looks at its MBL transition in the Fock space, it doesn't give any much difference from the random case. So you don't really see any difference. But we have not studied other kind of correlated disorders, so we don't know.
So about this non-ergodic extended and MBL, you said that the IPR or the delta typical, the scaling of those things don't distinguish. But would the distributions distinguish this? The reason I'm asking this is that you have in the NE phase, you have a localization length which is proportional to L or has some L dependence. Nevertheless, the states continue to be fractal, which would suggest that they live on some very sparse subgraph of your. So then the distribution should.
Yeah, so actually here, so that statement that I made was for the random case. So here actually there is a difference between the IPR fractal dimension and the self-energy fractal dimension.
But even if I stay within, so I just look at the IPR. So let's forget about the self-energy. So just the IPR scaling, both would show fractality, but will the distribution be qualitative?
Yeah, we have not studied the distribution, so I don't know. I mean, yeah, could be that the distribution. So we have, okay, actually we have studied the, we have studied the distribution of self-energy. IPR distribution we have not studied because IPR is limited, we have only small system size. But this Fock space propagator, we can go to larger system size. So there actually we see a difference between the distribution.
You see the difference?
Yeah.
Okay.
Okay. Arnab, you had a question? Yeah. Question.
So in general, we found two kinds of arguments that the thermal bubble thermalizes the thing versus thermal bubble might not thermalize the thing. So what would be your argument for non-thermal bubble localizing? So you are saying this is proximity effect of.
So you are saying this non-ergodic extended.
Right, right.
So here it is seemingly just they are staying as they are. I mean, like as if like they are not affected by each other. So you are still more or less, again, system sizes are too small. So but more or less the mobility age stays as they are in the non-interacting.
Yeah, so my point is, what is the argument for that? Why take the
I don't have any argument.
Here?
No, actually for that I don't have any argument. So the argument is only for this localization, full localization or full delocalization.
Okay, thanks.